Hello everyone, welcome back to my YouTube channel, Black Box Engineering. So I'm going to actually show you the full circuit design that I made today and explain some of the further things that I'm going to explain a little bit of how I came to the design and kind of show how the routing works so that it does what I wanted it to. So first of all, the audio spectrum consists of 7 fundamental frequency groups. They are sub-bass, which is 20 to 60 hertz, bass, 60 to 250 hertz, low mid-range, 250 to 500 hertz, mid-range, 500 to 2 kilohertz, upper mid-range, which is 2 to 4 kilohertz, presence, 4 to 6 kilohertz, and brilliance, which is 6 to 20 kilohertz. Most instruments struggle to reach the 41 hertz level, so in my particular design, I used a 40 hertz cutoff for the sub bass range. So technically, it's a 40 to 60 hertz cutoff there. And as I mentioned before, the full bandpass Butterworth filter is the starting point for the reference of the design. The one thing I didn't mention in the previous video for this application, audio AC waveform is extremely low in amplitude. It's like, I don't know, like 0.2, 0.3 volts or something like that. It's really, really low. So I actually added a preamp to the circuit here. Now this is going to look a little daunting, but it'll be a lot more simple once I talk you through the little subsections of it. So I'm gonna switch to my maker.io post that I made a while back, and I'm gonna also use a different diagram I made in KiCAD because I made a little bit more clear one a little bit later on. So anyway, so this right here is the full circuit, but the first section is literally just the preamp part. So I actually mixed up my positive and negative voltage here technically, but I think this side is supposed to be positive. No, this side of the op amp is supposed to be positive. No, negative. This side is negative, this side is supposed to be positive. So I have them technically reversed, but that's all right. I fixed it in my updated circuitry. So right here is the audio jack. You've got your right and left audio channels. They come through two 1 kilo ohm resistors, which technically does drop it further, but you need to do this for this particular circuit's called an adder circuit. We're combining two signals together and joining them into an op amp and boosting it through the gain here. So yeah, both signals are coming in. The combined, it would technically be mono audio in this case, would come into the positive side of the op amp, and then this resistor is at 3,000 ohms. This resistor is at 1, so you get gain off of that, and you loop it back into the negative side of the op amp, and then the output, which is the increased amplitude signal, is sent to the rest of the circuitry. So now let me just switch my drawing here. This was made in KiCAD, KiCAD. I'm not sure how to say it, but anyway, I think this is probably a little bit more clear, and it actually has like rectangle parts instead of weird triangle symbols for the op amps. These are more appropriate. The part that I chose for the preamp is OP275GPZ, so that's what I have here. And for powering the whole system here, I have something called a power brick. Let me go back to my post here and see which part that's what what the part is called here. So the manufacturer product number is from a company called Digilent. It is 410-294-A. The DigiKey part number is 1286-1108-N as in November, D as in Delta. So that's how I get power to the rest of the system. I believe it is I think it's a C input or a micro. I can't remember exactly, but all you have to do is plug in a external power, like any power supply that can provide 5 volts to the system, I believe. Let me just double check the data sheet here. Yeah, 5 volts. It takes 5 volts. And it's been a while since I've seen it. I think, yeah, if I remember right, I think it's micro USB, but I'd have to double check that at some point. Anyway, so that's how I'm getting power to the whole circuit here. It provides a positive 5 volt and negative 5 volt output, and the maximum current that it can produce is 250 milliamps, which is plenty for what this system requires. So anyway, and then let me just kind of talk about how I picked the op amp circuits here. So I'm going to just type in the OP275 GPZ. So this one is up to 9 megahertz of gain for the bandwidth, which is plenty for our purposes. It only takes 4 milliamps to power it, so again, fine. The current output per channel is 90 milliamps. The supply voltage goes from 9 to 44, minimum, maximum. I think it actually 9. Hold on, that doesn't seem right to me. Oh, no. Yeah, I don't think that's correct. I think the data sheet says -10 to +10, so I don't know. I think maybe the web page has some incorrect information here. Although maybe they're calling supply span something else here. I'm not entirely certain what they're. Anyway, you just need it to work within the expected like voltage voltage power that you're working with, the 5 volt, and according to the data sheet, 5 volts is within that range. So again, I'm not sure why the web page says something different. I'm not sure what they meant by that, but it's fine. I just know that it works. Okay, and then for the actual circuit, the Butterworth filter, I needed an op amp for the low pass side, the op amp for the unity gain buffer, op amp for the high pass side, and then the unity gain buffer for that side as well. So you would need 4 operational amplifiers. So I chose TL3474IN. Hold on. TL3474. That was strange. That might be a outdated number though, because I think now you have to buy a minimum of 1,000. So back when I purchased this was able to do one at a time. So honestly, you just have to find a different 4 op amp circuit that is a 14 pin thing that would work, that you can buy in singular amounts. I don't know why they changed that, honestly. It's probably because it's in a tube, but I mean, as long as you find something similar, should be fine. Anyway, so this is a 4 megahertz maximum of gain bandwidth product, which is fine for the speeds that we're dealing with. Up to 4 megahertz, we're dealing with much smaller stuff there. The current supply to power it is 3.5 milliamps times 4 channels. The output is 34 milliamps per channel. Input minimum is 4 to 36 volts, so 5 volts will work on it. And it's just a 14 DIP package. I'm sure that it'd be easy to find a one that didn't have a minimum order quantity of 1,000, but anyway, it's what I used originally. Anyway, so I need to show the layout of the routing of how this works. So what I did here, let me just make sure that I can see what I'm doing here. I took a screenshot of the LT Spice model and I drew little colored lines to see each significant circuit portion, just to make sure that I showed that they are equivalent, and it's going to be the same kind of action for each set of switches. The way that the actual physical circuit works is you would activate the left switch. It's a 4-pole signal throw switch, so you would activate one side and then the other to get, like, that's the sub bass. This side and then the other would be the bass, and then so on. And my challenge to myself is I wanted to use as minimal parts as I could think of. So I managed to get only, I think, a total of, how many resistors here? 1, 2, 3, 4, 5, 6, 7, 8, 9. That doesn't count. 10, 11, 12. Hold on, I'm not counting right. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. Only 14 actual resistors. And then there's a potentiometer. I guess you could count that, but that's just for the voltage divider on the output, because this boosts audio quite a bit. Anyway, so we see that this is the input audio. Left and right audio comes into this op amp through the plus, and then we've got our gain. So our output is on this line here. So let me just make sure I got the same colors here and run through. So we've got our output right here, comes up and through the switch. Let's say that this was a closed switch. We've got our first capacitor and then our resistor to the intersection, to this intersection here, and as well as this intersection. So we've got intersection. So then that's the same idea there. Then we have our positive input side, so the orange color. I'm just going to pick a much darker color because the orange looks a lot like yellow with the transparency here. So we're going to draw a line on this through the switch. It's closed, remember. Every other switch is open. So it comes down through this resistor, and this whole line here coming down is ground. So that's the same thing as this ground right here. And then we split off, come down to the positive input, which is exactly what we see here, right here. So there's that line. And now let's do the yellow output here. So we've got our output which is coming here to ground and to the negative input, which is what we see here. And then our line comes up through the switch to the intersection, or the node, I guess. And then we also need to go through another filter here, the CR. So comes up through the C, down through the switch, and then we've got a resistor to ground, and then it branches off from there to the unity gain buffer right here. So that's the same thing as the left side of this circuit for the bass, sub-bass frequency. Okay, then we need green. Okay, so our very next op amp is the one right next to it. So we see the feedback loop here. It comes down through the resistor, which is what we see here. We need to meet a node for this side and a node for this side, and a capacitor. So we come up through this blue bus, through the switch, and through the capacitor. So this is one node here, through the capacitor, and then it through another switch here, and then it meets this node. So node, the exact same thing that we see here. So blue, gotta switch colors here. So we need an RC at the first node into the positive. So we've got first node comes down. None of these are let's say that this was closed. None of these are closed. So it doesn't want to go down this way. Instead it goes through the resistor and goes up. And we need a C, so it comes through the closed switch, through the resistor to ground, and it branches down and to the positive side of the other side of the op amp, which is what we see right here. So this is the blue. And then we need like a magenta pink color. I think it's more like a purpley, if I remember right. So from the op amp output, remember we need the gain, so it comes through the resistor to the negative side and to ground. And then from this node it comes up through the bus all the way up to the node, which is what we see right there. And then we need the final stage, the last filter. So another R comes to this capacitor, which goes to ground, and then it branches off through the bus, down, up to the unity gain buffer, which is what we see here. So this is that line. And then finally we have the cyan color for the actual output, which is right here. The very last op amp comes through the voltage divider to ground, and then technically it's mono audio, so both sides are just passed to the same left and right jacket. So technically this isn't stereo compatible, just turns it into mono, but honestly you can't really tell the difference. So anyway, and let me just choose another CM. let's choose, I don't know, uh, let's say like a really dark purple to just show you that we are dealing with a complete path here. Yeah, I know it should be red, but it's fine for what I'm talking about here. So anyway, this red and purple are the same. I'm just showing that technically the path from the input to the output is clear. It just goes through a lot of different stages to get there. So yeah, that's pretty much the flow for the rest of the switches. It's just a little bit harder to imagine because now I have to just kind of show you how each stage. I'm not gonna go through every single stage to show you the flow of the lines here, but anyway. So yeah, preamp to our high pass to the low pass, and then to the sorry preamp, high pass, unity gain, low pass, unity gain, output. That's literally the whole circuit. So it looks complicated, but it's only the routing that's complicated and not the actual idea of the circuit. Technically, there's a lot of math behind it, but it's actually a pretty simple analog circuit if you think about it. Anyway, so all right, so I just wanted to go through just a second like path just to kind of show you how the rest of the flow works. I'm not going to go through each step like I said. That would take too long, so just going to go from the output to we're going to use the base low pass pair here. So we need a red, so that comes from the output here up through here. Since this is now open, it needs to go down to the next available path, which is down this way through the switch, through the capacitor, and then this needs a resistor, which is this resistor. So then that's equivalent to this first red line, because we've got a node here and a node here. So next color is orange. Use a darker orange, so it's not too similar. This path comes off of this side through the switch, through the capacitor, up to the bus, going this way. Resistor to ground, and then this path goes back to the positive side of the first op amp. Then our next color is yellow. I'm going to switch this to bright yellow. Yellow comes from the output of the op amp, so come through the resistor to the negative side and to ground, and then it branches off this way going up, but since this is open, it needs to come down through this bus right here, through the switch, and back to the node where we need it, because we see that right here. And then the last step, of course, is the going to the unity gain buffer. So the last path is, again, we need a capacitor resistor. So through this capacitor, through the switch, up through the bus, through the resistor to ground, and then it also branches back to the unity gain op amp here. The next color that we need here is green for the output of the unity gain buffer. I should maybe just switch that over to like UGB or something, or I could just say buffer in this case. So we've got output from the buffer through the resistor coming up through the bus, but now we have these switches closed and this one open, so it has to come through this path, through this capacitor, up through the switch, which sees this node and this node, which is the same thing as this node and this node. So the next color here is the blue. Which comes off the first node here, which would be here. And in this case it goes up through the resistor. Does not want to go this way because that's open. So it needs to come down through the bus and through the switch to ground. And we also need it to route down to the positive side of the op amp on that side, which is what we see right there. Next color is magenta. That's actually cyan, but it's fine. Magenta. Magenta comes off of the output. So the output is here. Comes through to the negative and this resistor, and also this resistor to ground for gain. And then it comes off of this node up through this line to this bus, which goes up, which then it comes up and it technically overlaps because it needs to go to the same node. So that's why we have that, because it meets up with this signal here, and we need it to go to a final RC. So this is this resistor, doesn't want to go this way because this is open, comes down through this switch and this capacitor, not resistor. I keep on saying the wrong word there. Capacitor to ground, and then finally we've got our final unity gain buffer right there. Sorry, it gets kind of complicated when it comes to going to the same node because it's overlapping basically. This junction right here is the same thing as this node, so this is like a giant node. It's just a little harder to wrap your head around, that's all. And then finally we've got our I used the wrong blue. This is supposed to be a darker blue, so I'll just use dark blue, the final stage here. So we've got our unity gain. Oops. Let me draw to our voltage divider here, to ground, and to the output. So in general, each side of these switch banks and stuff do have similar layouts so that it can do the exact same thing. It just each time it goes to a slightly different path because of how the buses are laid out and whatnot. So yeah, it's actually not too complex of a circuit technically. There are far more complex circuits out there. My next video is going to probably be a camera pointing at how to set it up on a breadboard so that you can actually see what it does. I'll have to find some royalty-free music to test it on again. So anyway, thank you for watching. Like, comment, subscribe if if you've got questions. And yeah, just this stuff is very interesting to me. I always like figuring out how to do routing and coming out with designs. This is probably my most complex design to date. So anyway, see you in the next one. Bye.